All right, so today we're going to continue talking about the Heine-Borel theorem. Let me remind you where we are in our discussion of this. So remember, we say X is compact if every open cover of X has a finite subcover. And well, one of the reasons we like compact spaces is because of the boundedness theorem, which we proved last week, which says that if X is compact and you have any continuous function from X to the real numbers, then so this is continuous, then this implies F is bounded. And moreover, achieves a maximum value. Okay, and so the main topic for today is the Heine-Borel theorem, which gives a characterization for compact subsets of Rn. So compactness is something that's defined just for an arbitrary topological space here, but Heine-Borel theorem characterizes compact subsets of Euclidean space. And it says, so you have X in Rn is compact if and only if X is closed and bounded. So last time we proved this direction, and today we'll prove the reverse direction. Okay, so closed and bounded implies compact. So the proof of the reverse direction is going to reduce to two results. Let me state them now, and then explain their relevance. So the first says that if X is compact and a subset of X is closed, then this implies that A is compact. Okay, so in brief, a closed subset of a compact set is itself compact. So we'll prove this in a second. And the other result is that cubes or closed rectangles are compact. So I've stated this for the unit cube, but any closed rectangle is topologically equivalent to this. So, so hence also a closed rectangle, which could write like this. This is compact. Okay, so before saying anything about these two results, let me explain how, using these two, we can finish the proof of the Heine-Borel theorem fairly quickly. So here's So, okay, so we're proving the reverse direction. So assume X is a subset of Rn, which we know is closed and bounded. We want to show X is compact. So usually one way to show a set is compact is to show that it satisfies this definition. But frequently that is a pain to do, difficult to do directly. And so we're not going to do that. We're going to use these two theorems. So first of all, X being bounded means, well, X is contained in some large ball centered around the origin. And so then X is also contained in some large rectangle. So this implies X is contained in Q for some closed rectangle. Something like this. And then, well, Q is compact by the theorem, and X is closed by assumption, assuming X is closed. This implies that X is compact by the proposition. Right, so by the proposition, we just say that here. And here, the theorem is being used here, Q compact. Okay, and that's what we wanted. Okay, so once we know these two results, Heine-Borel just sort of falls in our lap. So that leaves us with the task of understanding why these two results are true. Okay, so let's start with the proposition. The proposition is relatively quick. The theorem will take a little bit more time to explain. Okay, so right, so we need to show that A is compact. So we're going to do this using the definition. So we start with an open cover of A, and we need to find a finite subcover. So let's let U be any open cover of A. And so somehow we have to find a finite subcover. And the assumption that we have to work with is that A is contained in, so let me draw a little picture here. So we have A is contained in some X, which is compact. And what we're given is, so we have some open cover of U, of A. U is an open cover of A. We don't really know what it looks like. Something like this. Well, we know that X is compact, and we'd like to use that. So if we could, so what we're going to do is increase this open cover of A to an open cover of X. So so then if we take U together with the complement of A, this is an open cover of X. So A is closed, so its complement is open, and this covers X because, well, every point A is covered by something in an open set in the script U, and the rest of the points are covered by the complement of A. Okay, and so then X compact implies that there's a finite subcover let me write it this way. U1 up to UM together with X minus A. We know that X minus A is going to be in this finite subcover because, well, as long as A is a proper subset of X, there's going to be some, well, yeah, maybe this is in there, maybe it's not. If we throw it in, it's still a finite subcover. But in any case, this implies that U1 up to UM is a cover of A, since, well, points here don't help you cover A. So if this collection here is a cover of X, this is a cover of X, then points of A must be covered by points here. Okay, and that's exactly what we wanted. So we found a finite subcover of A. Okay. All right, so now I want to explain so now we need to explain this theorem. Let me start a new section for this. So compactness of the cube. Okay, so there's one main ingredient that I need to tell you about before we can start to discuss this result. Which is called the onion ring theorem. And it says that if Qi in Rn is a family of nested closed rectangles, then the intersection of the Qi's is non-empty. So here nested means that Qi contains Qi plus 1 and so on. So that, right, so this is the statement. So the picture is, let me just draw a picture in dimension 1. So you have some nested, here closed rectangles are just closed intervals. So here you have like Q1, and then inside that you choose some other closed interval Q2, and then some Q3, and so on. And the statement is, well, I mean, these don't have to be proper subsets. So maybe Q5 is equal to Q4. But the statement is the intersection has to be non-trivial. And it's called, okay, so that's the statement. It might seem intuitively obvious from the picture. And it's called the onion ring theorem because, well, the two-dimensional version kind of looks like slicing open what you see when you slice open an onion. So maybe instead of rectangles, I'm going to draw two-dimensional balls. They're topologically equivalent. So if you have some nested sequence of balls, then they have to have some center. Okay, so this is the onion rings. So another name for this theorem is the nested interval theorem. But I think onion has a nice ring to it. Yeah, so the theorem follows from the case n is equal to 1. And so in the case n equals to 1, we're just talking about nested intervals in the real line. And the case n equals to 1 follows from something called the least upper bound property for the real numbers. So I want to tell you what that says. Least upper bound property. So let's do that on a new page. So, okay. So this says that if let me say it just loosely first and then explain it in detail. So the statement is every non-empty, subset A of R that's bounded above has a least upper bound. Okay, so there's some terminology I need to explain. So we say A in R, a subset, is bounded above if there exists some number B, say, so that A is less than or equal to B for all A in A. Okay, so there's some point after which, yeah, so sorry, let me finish the definitions, then talk about examples. You say that B, and here we say B is an upper bound. And we say B is a least upper bound if it's smaller than any other upper bound. So if there exists, so if B prime is another upper bound, then B is less than or equal to B prime. So B prime is the least amongst all upper bounds. So for example, well, A is Z in R. This is not bounded above. The integers is an unbounded subset of the real numbers. On the other hand, if we were to take A, say just the interval 0, 1, this is bounded above by any number greater than 1, greater than or equal to 1. And it has least upper bound 1. I mean, 1 is an upper bound. It's greater than or equal to anything in this by definition. And it's the least possible upper bound. Okay. So this least upper bound property of R, you should think of it as, well, it's either a definition or a theorem. I mean, as it turns out, R is the unique ordered field that satisfies this least upper bound property. So for example, well, the rational numbers, well, okay, I don't want to go too far down this road. So there's this property for R, which is the least upper bound property, which is quite important and underlies a lot of the results that you know from calculus or analysis in one variable. But okay, this is an analysis class, so I don't want to really say too much about it. But what I do want to do is to use it to explain why closed rectangles are compact. Well, oh, right, sorry. So, I mean, the way this comes up is in proving the nested interval theorem, the onion ring theorem, and the onion ring theorem is what we're going to use to prove this. Okay. Okay, so the proof technique here is what's called the method of bisection, which will, hopefully this will make sense as soon as we see how this goes. So we're going to proceed by contradiction. So suppose the cube is not compact, which means there exists an open cover U with no finite subcover. Okay, so there's no finite subcover for this open cover. So then, well, what we're going to do is so the main observation is that if you have a cube and you break it up into quadrants, then you get smaller cubes, and you can apply this assumption to the smaller cubes. So consider, let me say, divide. So let's divide 0, 1 into quadrants, like I pictured here. So, well, by assumption, one of the quadrants is not covered by finitely many elements of script U. So we're starting assuming that finitely many, there's no finite collection of open sets in script U that covers the whole square cube. If there were finitely many that covered each of these quadrants, then there would be finitely many that cover the whole thing. You just take the union of those finite collections. So there must be at least one of these, say Q1, which is not covered by finitely many elements of U. And now anything you can do once, you can do infinitely many times. So we're going to repeat this to get, so then we start with Q1, and it has this open cover with no finite cover, and we can divide it into quadrants. And then find some Q2, which is smaller and has the same property. So we repeat to get a sequence of, or let me just say, we get nested closed intervals, or nested closed rectangles. They're cubes, but okay. Qi plus 1 in Qi. So with the property that, so first of all, Qi is not covered by a finite subset of U. And the second important property that Qi has is that the diameter, or let me say the side lengths of Qi are 1 over 2 to the I. They're going to 0. So these cubes are getting smaller as we proceed. Okay, so now what do we do? So we've found this collection of nested rectangles, and so we can apply the onion ring theorem. So to conclude that there exists some point in the intersection of all of these. Okay. So now, so we take the intersection of all of these cubes, oh, excuse me, and it contains some point. That point must be contained, so take some open set in the cover. So let's take U in script U with Z in U, and we're almost there. So let me try to fit it here in this last line. So U is an open set around Z. Since U is open, there's some small ball around Z which is contained in U, and that ball must contain the closed rectangles which are sufficiently small. Since the size of these rectangles is going to 0, well, we conclude that Qi is contained in U for I large enough. But this contradicts, so let me just say this is by property 2, but this contradicts property 1, that the Qi's are not covered by a finite subset. Here we found a single open set that covers some Qi's. Okay, so this is a contradiction, and from this we conclude that this open cover U could not exist. Okay, so like I said, this is the method of bisection, which is sort of a useful kind of argument that appears in analysis. Okay. So I want to finish this part of the lecture with some examples, more examples of compactness. So now we've finished the proof of Heine-Borel. We reduced it to proving these two theorems, and we just finished the last of these. Okay, so I want to, as I said, give a couple more examples of compactness. So the annulus, let's take this particular annulus Z in R2 with the norm of Z bounded between 1 and 4. So this looks like this. This is the circle of radius 1 and the circle of radius 2, and A is the region between, including the boundary. So this is compact since it's closed and bounded. But if we were to take instead B to be, if we change this definition just slightly, so now we don't include the inner circle, then this is no longer compact. And well, one way to say that it's not compact is just because it's not closed. So you have points, points on the circle are limit points of B, but aren't in B. Another way to say it is, well, here's another way to prove a set is not compact. You find a function which is unbounded, a continuous function on B which is unbounded, real valued. And in this case, you can take something like this. Absolute value of Z minus 1, this is continuous and unbounded. This function point of view for showing properties of Rn is, it's a useful point of view to take. And well, I mention it here because it also will help on some homework. Okay. A couple more examples of compact sets. So the Cantor set. So maybe you've seen this before, but so it's defined in the following inductive way. So you start with the interval from 0 to 1. Let's call that C1. And then you remove from this the middle third interval to get C2. So that here we have 0 to 1/3, 2/3 to 1. You have these two intervals, and then you repeat on each of these, removing the middle thirds. I haven't drawn this to scale, so this is like 0, 1/9, and so on. 2/9, 1/3, and so on. And then C is defined, the Cantor set is defined as the intersection of all of these. And well, it's closed, it's compact because it's closed as the intersection of closed sets, the intersection of any closed sets is closed. This is complementary to the fact that the union of open sets is open. And it's also bounded, sort of in an obvious way, since we're just working in this closed interval. So hence compact. Okay, so this is an interesting example that maybe will come up later. Okay, one final example. The Mobius band. So M, which you obtain from starting with some closed rectangle by gluing. So this is compact. And the reason, let me sketch the reason, which we don't quite have everything at our disposal to give a full argument here. But, well, so there exists a map let me say, not say there exists. There is this map. It's a concrete thing. It's the gluing map. Is a gluing map from the square to M. And well, so we haven't carefully defined a topology on M, but however we define it, the main thing we want about this topology is that this map is continuous. So which is continuous. So let me just put in parentheses, we need to topologize M. And we'll do that next week, or maybe at the end of this week, with what's called the quotient topology. But once we do that, we'll have this continuous, map, and since this is, the square is compact, then its image under a continuous function is also compact, which is something we showed. And so M is compact. Okay. All right, there's one other topic I want to start today very briefly, which is connectedness. So for now, we're done talking about compactness, although it'll come up later. Again, as a tool, we'll want to use it. So connectedness. So this is a topological invariant or topological property that captures the number of pieces or components of a space. So let me just give you some spaces that are connected and not connected, or we'll say disconnected. before giving you the formal definition. So what is this trying to capture? Well, okay, so some connected spaces, I guess mostly we've been thinking about connected spaces. So R, Rn, the interval, I mean, each of these seems like they have one piece. Similarly, the two sphere, the torus, etc. Some disconnected spaces, well, I mean, you can easily find disconnected subsets of the real line. I don't know, like something like this, or maybe the Cantor set is a good example. Cantor set has many pieces. Or yeah, I mean, I don't know, disconnected spaces, it's kind of boring because they're unions of connected spaces. So I could say like the union of a sphere and a torus, or maybe something like the boundary of an annulus is disconnected because it's two circles here. There's two pieces to the boundary. Okay, so this is the notion that we're trying to, that we will want to formalize and understand. So let me just give you the definition, and we'll work with it a little more next time. So we say X is disconnected if there exists open subsets U and V, so that X is the union of U and V, and U and V are disjoint. And they should be non-empty. Okay, so X is expressed as a union of two disjoint non-empty open sets. So it has these two pieces. U and V are capturing the idea of pieces. Okay, so I think I want to stop here basically. So next time we'll think a little bit more about connectedness, and well, here are some examples. That we'll discuss. So whenever you make some definition like this, well, you want it to capture your intuitive notion, and we'll see that with this definition, these spaces are connected and these spaces here are not. But then you also want to think about what are the more unusual examples that this definition applies to. So, so for example, is Q connected with this definition? Or what about GL2R, which appears on the homework this week? These are invertible 2x2 matrices, which is to say that the determinant is non-zero. Is this connected or not? And another interesting example we'll think about is what's called the topologist's sine curve. So it has, let me not say it has two pieces. It's made up of two components. So the first is the graph of sine 1 over x. Here, this is the graph of sine 1 over x, which has this weird behavior at the origin. This just oscillates indefinitely on smaller and smaller periods with smaller and smaller periods. And then to this, we add the this interval here, 0 times -1 to 1. which is basically the set of limit points of this graph. Okay, so is this connected or not? I mean, it kind of looks like, and as I was describing it, so there's these two pieces, but on the other hand, then they kind of fit together in a tight way. So we'll want to understand, this will be a good example to think about. All right, so that's it for now.